Okay, so again, we want to do three main things today. A couple new examples of improper integrals. A proof involving something called the comparison test for improper integrals, and then hint at some applications of improper integrals that we will get into more depth in chapter 8 on. So on Monday, we integrated this function from 1 to infinity. And we saw that the improper integral diverged. New improper integral today, it's not going to involve any infinity, but it will involve a spot 0 where this function has a vertical asymptote. If you graph this integrand function 1 over square root of x, it's got a vertical asymptote at 0, which makes sense. You'd have 1 over something approaching 0 as x goes to 0. So it's still improper because this region goes up forever and ever. And it's not clear then whether it will converge or diverge. The area that I'm shading here may or may not be finite. It goes up forever in extent. It may be finite and it may not be finite. As with improper integrals involving infinity, we have to calculate this as a limit. And if the limit exists, we say the improper integral converges to whatever the limit is. And if the limit does not exist, we say the improper integral diverges. Same language. But now it's the bottom limit of integration that's going toward the place where we head off to infinity. I'll call the bottom limit A. A is going to 0. From the right, if I want to be a little bit more specific, I put a plus sign to the right of the number 0. That means A is approaching 0 from the right, which in this case happens to be through positive values as well. But I could put a plus sign to the right of the number, even if the number itself was negative, and it would still mean from the right. Keep the 9 as a 9. To do this integral, it does not involve a natural logarithm. It's best to write it as a power function, x to the negative 1/2 power, which means then you're going to add 1 to the exponent to get positive 1/2 power and divide by that same number 1/2 to do the integral. X to the positive 1/2 power, negative 1/2 plus 1 is positive 1/2. Divide by that same number. Evaluate from A to 9. Dividing by 1/2 is the same as multiplying by 2. So I get 2 times the square root of 9 minus 2 times the square root of A. Square root of 9 is 3. 2 times 3 is 6. That's a 6. What happens to square root of A as A goes to 0? The answer is supposed to be easy. Goes to 0. Right? You take the square root of 0.1. It's still close to 0. It's actually bigger than 0.1, but it's still close to 0. Square root of 0.01 is 0.1. This does go to 0 as A itself goes to 0. And therefore, the answer is 6 minus 0, or 6. This improper integral does converge to 6. We can interpret that as the area under this graph, even though it goes up forever and ever, is this finite number 6. That's one way to imagine it. It's not that you can literally draw the region in an infinite extent. It essentially is just that this limit exists. You might question whether this is useful. We will see examples probably next week and certainly later in chapter 8 where this is useful. And I will hint at those examples at the end of class today.